This is Pete Goldstein from Ceradyne. He's going to be talking to us today about advanced ceramics. And I guess I'll let you go ahead.
Okay. First off, I want to say thanks for everybody for coming to listen to me talk about something that's may or may not be related to Google so much, but it's to me, I find it very interesting as the world of advanced ceramics. So ever since I was a young boy, I was always interested in the world around us. And I remember when I was about 4 years old, we had a racetrack. We had a car racetrack with a remote control, and the cars would zip around it, and they'd stay hooked onto the racetrack. I never knew how until after I used it a couple times, I picked up the car and looked underneath, and I saw this gray rectangular material. And I was wondering, what is that? So I ended up taking apart all of my toys, and I took apart all of the cars just to play with the magnets. And that kind of sparked my innate sense for the interest of the world around us. Eventually, I watched Mr. Wizard, and he taught me how to make a little fire by harnessing the sun's rays with a magnifying glass. And ever since then, I've always been interested in science and technology. Eventually, I went to college, and I studied material science and engineering at the University of Florida. I earned my bachelor's and master's there, and focused in ceramic engineering because my professor for the Introduction to Ceramics course was the most interesting of all the courses that I taught. I figured if he could do it, so could I. And so this picture here shows ceramic that we make at Ceradyne that I took home to use in my home glass blowing studio to see how hot you could get it. I'm going to talk a lot more about this material a little bit later, but I just want to show you this picture and show this material being heated up and then the travertine tile underneath cracking, because one material won't crack and the other one will. You'll see why in a little bit. So the way this talk is going to work, I'm going to go to the beginning of mankind, really, and kind of take everyone through a little trip of material evolution and its effect on technology. And then I'm going to get into the advanced technical ceramics world and talk about different materials that most people don't even know exist and some of the applications that they work in. And then I'm going to touch on the future a little bit. Now this picture I have shows the game of rock, paper, scissors. So in that game, rock beats scissors, and paper beats rock, and scissors beats paper, which is the way the game works. But in the evolution of materials and its effect on mankind, quite the opposite is true. So in the beginning, a couple million years ago, man started to evolve a little bit. And the first primates or cavemen, what have you, had wood tools. They had little sticks and things of that nature. After about 1 million years, they evolved into modern caveman. Modern caveman used rocks and stones to make tools. They used flint to learn how to make fire, and that really sparked the first step towards man's effect on the world around him and kind of changing the way the course of time. So the key thing here is that man used stone axes and made knives, and all these materials are somewhat considered a ceramic type material. The word ceramic is a very ancient word. It actually comes from the Greek word keramos, which means pottery or potter, and that actually dates back to the time of Sanskrit, which means burnt earth. So it took about 1 million years for mankind lighting the fires to actually realize that there was something underneath that after the fire burnt in that one area for so long, there were some very hard materials. And that was where the first early ceramics came from. And they date back, the earliest ceramics that anybody has really discovered, it comes back about 24,000 years to, they found some figurines in Czechoslovakia. So this picture is actually of some ceramics pottery that is maybe from the 5th century BCE. So it took basically 1 million years of experimentation just to figure out how to make ceramics to begin with. And from there on, at about 8,000 BCE, so it took about 16,000 years to develop glass, which was really kind of found by accident in the northern Egyptian area. When somebody heated up the kiln, or that was making the ceramics, which had the right amount of sand and calcium oxide and sodium carbonate in the area, and they found a nice, pretty glassy glaze on that ceramic. And then it took about another 6,000 years to figure out how to remove the glass from the ceramic and make each material separately. And that was what was considered still the Stone Age time. In about 3500 BCE, people discovered how to make metal, and we entered the Bronze Age and kind of exited out of the Stone Age. This material was manufactured and made probably when somebody heated up their little pottery kiln a little too hot and had the right elements inside, and they noticed that the metallic, the bronze, which is made out of copper and tin, flowed to the bottom and kind of came out. So this is where the scissors beats the rock, because the people that ended up developing the Bronze Age and the bronze weapons and jewelry end up overtaking the people that had the stones. So the newer technology took over the older technology. Actually, I was in Israel a little bit ago, over in the Timna Valley, which is in the southern part of Israel, or the northern part of ancient Egypt, and I got to witness some of these old smelting furnaces firsthand, and I found this very interesting. Especially, I want to include it in the talk because this is actually real artifacts, and this is what the old metalworking kilns look like. And they wouldn't have existed without the ceramic refractory type materials on the outside. It was heated up to about 1,000 degrees C with the ore inside, and once it got to the right temperature, all the copper would come out of the bottom. So this happened at the same time that the Iron Age started to come about. So people ended up developing and realizing that you could make steel by melting certain other materials at higher temperatures, and that this material was even stronger than the bronze. So the people who had the steel technology ended up kind of conquering the people around them, which is another step on the kind of evolution of mankind and materials. So it took a long time to go from caveman lighting fires to survive to making steps every few thousand of years to develop different materials. So now in the past couple hundred years, more advanced or more typical ceramics have come about. And most people, when you think of ceramics, you think of toilet bowls or coffee mugs or roof tiles. And those are very important materials because they shape the world around us. But the ones I'm going to talk about are a little bit more advanced. But before I get to that part, I want to kind of just ask everybody, what is a ceramic? Does everybody kind of know what a ceramic is? Kinda? Yes, no? This is a question all my professors always ask me in college, so I figured I'd just share with you the official definition, is that it's typically an inorganic material that has ionic or covalent bonds, and it's typically made out of metal and a gas combined, and it's a very inert type material. There's a wide variety of different types, and they're usually crystalline in nature, but they also can be amorphous. And this picture is of a typical ceramic, and this picture here is of an advanced ceramic called silicon carbide. I'll explain that in a little bit. So the reason why advanced ceramics haven't been made until very recently is because it takes a lot of technology just to process the materials. You start with a powder that's very dense and hard. You can't do much with it until you compact it. Then you have to heat it up to the right temperatures to where each individual particle wants to become one big particle. And due to the thermodynamics of each particular material will determine the amount of heat and energy that you need to put into creating that ceramic. Now, ceramics are key enabling technologies for pretty much everything around us today. And I think of them as the unsung hero of the materials world because not too many people know what they are, take them for granted, or don't realize just what they do. But one of the biggest ceramics out there are just refractories that enable furnaces to run at higher temperatures. Without them, you couldn't make fiber optics. Without that, there'd be no internet. And I think we all hold that very near and dear to our hearts. computers in general, even before modern computers came about, there were the vacuum tubes, and you had to make the glass in the same type of furnace. And even glasses are considered a type of ceramic material. Cars, the same thing. You have a spark plug inside the engine. It is made out of a very insulating material called alumina. And the same goes for airplanes and electronics, TV, radio, and everything else you can imagine. And if anybody has any questions afterwards, feel free to ask. Now, the difference of regular ceramics versus advanced, what we call advanced technical ceramics, are that advanced ceramics can go up to very high temperatures. Their properties are much stronger than steel, and they're much harder. The hardness is up to 3 or 4 times that of steel. It's a very lightweight material, and they're extremely resistant to certain chemicals, or pretty much almost all the chemicals out there, whether they're bases or acids, and that becomes the key in lots of different processes, such as even semiconductor fabrication. And electrical properties depend on the exact material, and I brought a wide variety of things to show everybody at the end, and we can talk about the differences of all of them in a little bit. This is a few pictures of what advanced technical ceramics look like, and what we consider to be what we consider those materials to be are really typically non-oxide materials, because your typical ceramics are oxides like alumina oxide or zirconia oxide. Then the more advanced materials are materials that aren't found in nature. This picture right here is of boron carbide. This is a powder of boron nitride. This is a piece of silicon carbide. This is a composite material of a couple different borides. And this is also silicon carbide. So in general, in the ceramics world, the non-oxide ceramics are all the nitrides and the borides and the carbides. So Ceradyne, I didn't really mention, is the company that I work for. I've been working there since I graduated college as a sales engineer, so I really work on a lot of interesting type projects, and I'm going to discuss a lot of those with you guys, at least the ones that we can talk about. It's a company that's about 40 years old. The founder founded it in his garage about 40 years ago, and he's still the CEO, and it's all we make are advanced ceramics, and not too many people know about it, so that's why I like to share, and I'm glad that all of you are here and listening. And ESK Ceramics is a European company located in southern Germany, and they're part of Ceradyne now, and they've been around since the early 1920s, so they've got an incredible amount of technology and materials, and those will be some of the materials that I talk about in a minute. So advanced ceramics are used in places such as the aerospace industry, nuclear waste containment, which is what this huge, what you call a casket is, armor, which is what this is called the Bull. It's a mine-resistant vehicle. And actually, I brought a sample of our body armor too, which is made out of a few different hard ceramics. And it's used in the semiconductor industry. They're used as heat exchangers for the chemical process industry, and quite a variety of other places. And we'll get into all the details right about now. So the aerospace industry uses a material, well, they use a lot of different high-tech materials, but one material in particular that I'm personally very fond of is called silicon nitride. Its formula is Si3N4, so there's 3 silicons and 4 nitrogens, and it is a very hard, very tough ceramic, and it's a very strong insulator. And it's used, one of the neatest things that it's used on are the nose cones for missiles that need radar guidance, because it's a very thin, tough material, but it can transmit RF frequency. So it can communicate with whatever it needs to communicate with. It's also used as the spark plugs for airplanes. So anytime you take a trip down in a DC-10 or a 737, chances are that the spark plug is made out of this material, because it can withstand the harsh environments of a jet engine. And that's actually why this material was developed back in the 70s. One of my old bosses, his name is John Mangles, worked at Ford and led a team of about 30 scientists and engineers for about 20 years just to develop this material. So that way it could be used to create efficient power in jet turbines. This picture shows the microstructure of silicon nitride. The grains are these dark gray areas. They're elongated, somewhat needle-shaped, in comparison to typical ceramics, which are more boulder-shaped, which have more boulder-shaped grains. And that's what accounts for its toughness, because you have millions and millions of these microscopic needles all interlocking, and it creates a very, very good properties of toughness and compressive strength and low friction. Another interesting material is boron carbide, which is this picture right here. And I brought a sample rock also, so you guys can come up and take a look afterwards. Boron turns out to be a neutron absorber. So it's used in areas where there's high radiation. And the material boron carbide has 4 borons and 1 carbon. So it's got a very dense amount of boron in it. And when you mix it with aluminum, you create a composite material that absorbs radiation, which is very important because there's a lot of nuclear power in the world, and after you use the fuel rods, you have to store them somewhere. And there's a lot of spent nuclear fuel in the world that needs safe containment. So this container, made out of a composite of boron carbide and aluminum, can store spent fuel for a very, very long time. Another area that boron carbide is used in is military armor and vehicle armor and body armor. And that's actually, I brought a sample up here. The material is so hard that when an AK-47 bullet hits it, the bullet physically shatters. And then the ceramic also shatters in a local area. And the way the whole thing ends up stopping the bullet is because it's backed with a Kevlar-type material. And the really interesting thing is that, I don't know, I've met quite a few people who have been in Iraq wearing these vests, and it saved their lives. One guy had a machine gun, and he got hit right in the gun and 5 bullets right up the center of his chest, and he's still living to talk about it. And another guy I met just 2 weeks ago at an art show, I was talking to this guy looking at a painting, and on his leg, he had a big scar, and I said, "What's that from?" And he said, "Well, I just got back from Iraq a little while ago, and the vehicle I was in drove over a mine, and it exploded, and it tore up his legs and his arms, and he had the really wicked scars. But luckily, the plate stopped all the shrapnel that was going into his chest, and it saved his life." And I just find that really incredible. The material is so hard, it's almost as hard as diamond, and the way that you manufacture this material is extremely energy intensive. The closest thing on the world to the area that you can make boron carbide is a volcano, and we actually had to get some of the world's top volcanologists out to help us design this furnace that we used to make it. And it takes about a month to make a 40-ton brick of boron carbide. Then you have to break it down with jackhammers and different attrition-type mills to make very fine powder. Then it has to be processed with lots of chemicals to make it have the right composition. And then it has to be heated back up to over 2,000 degrees C and compressed with with hundreds of tons of pressure. And after it goes through all that, you get a nice plate of this material that'll stop a bullet. And I just find that incredible that there's so much energy that goes into manufacturing it, and that kind of, in the conservation of energy state of mind, that's why it stops bullets. There's so much energy in it, it can withstand so much energy. One area that silicon nitride is used in is our car engines, or diesel truck engines in particular. There was a time in the development of trucks that most engines were failing after about 50,000 miles because one of the key components, the cam roller, which was made out of steel, would gall and spall and end up failing and cause a Mack truck to shut down. By replacing that material with silicon nitride, the trucks are able to run for millions of miles. There's an extremely low coefficient of friction between silicon nitride and steel, and it's very lightweight, so the area that it's in the engine oscillates extremely fast, and it saves a lot of energy. Another area are race cars. We make parts that go in race car engines. And I met a guy who has Porsches. He races the Porsches, and he's had one of these silicon nitride lifters in the car and raced it every week for years, and it has worked incredibly. Another interesting product that ceramics and diamond is actually used are these friction shims, which are these pictures down here. In that material, there's a very fine monodispersed layer of diamonds that's embedded in also another ultra-hard material, and they're used to stick components together when there's any sort of rotational speeds, such as in the car engines between the camshaft and the flywheel. But in lots of other applications too, when something is spinning really fast and you need to transfer the torque to another part, the diamonds stick into both sides and really hold everything together and increase torque by about 300%. Some of the pictures didn't come through. Also, medical products are made out of ceramics because ceramics are biocompatible. We do make braces out of ceramics that are translucent. It's actually a line called Clarity offered by 3M, and it allows people to not have the big metal mouths that I had when I was about 12 or 13. So if I knew these existed, that would be pretty cool. But another area that ceramics play a part in that's near and dear to my heart and probably everybody else's are the evaporation boats. This allows this thin silver lining to be placed inside potato chip bags. The way it works, the material is very it's wetted by aluminum and it's not corroded by aluminum. It's used in a furnace where a rod of aluminum is placed onto it at a high temperature, and the aluminum melts, or whatever metal you put in there melts and spreads across the top and evaporates off of it, and it coats polymers to make this very nice silver lining and allows your Cheetos to be crunchy. So I always think that's pretty cool. Now, another area is the industrial area. The industrial wear products group of companies rely on advanced ceramics to take their processes farther and be more efficient. Silicon nitride, there are three materials that are used in these kind of applications, and that's silicon nitride, silicon carbide, and boron carbide. All are used for their very hard nature and their chemical inertness. One area that's very interesting also are windmills and windmill bearings. With the need for more efficient and greener electricity, everyone is looking for different ways of attaining that. And the windmill bearings, by having a silicon nitride ball in between the two metal races, allows for bearings to last a very long time. Some issues that exist with windmills, if you have ever driven across down the highway and seen a bunch that are stuck, is the fact that they create huge amounts of static electricity on the blades. That static electricity jumps across the outer race through the metal ball to the inner race when you have metal bearings in there. And when that happens, it creates a little pit, and the whole bearing fails. And then how do you replace a ball bearing up on a windmill? It's a lot tougher than replacing something in your bedroom or your fan in your ceiling. So silicon nitride, again, is an excellent material because of its low wear and low friction. And also, every piece of paper, or mainly every piece of commercial paper that you touch, has touched a piece of ceramic in its lifetime. The paper mills start with wood, and they go process the wood with chemicals and liquids, and eventually a huge sheet of pulp moves at about 60 miles an hour over various areas that remove a little bit more and a little bit more of the water. Eventually, when the paper has about 95-99% paper pulp, it has to go through its final stages of manufacturing to suck the final bit of water out of it. And at that point, it rides over these huge 30-foot-long beams of silicon nitride and silicon carbide. No other material can survive that environment. Steel and metals would rust, and they wear away quite fast. The ceramic lasts for many years, and in every major paper mill in the world, it exists, and it helps make the paper. Another interesting area that silicon carbide is used are in fluid handling circumstances, such as pumps for chemical pumps and also water pumps in every car engine. This material is very hard and also has a very good chemical resistance, and it can withstand pretty much any chemical out there. It's used in pumps and in many chemical manufacturing plants where nothing else survives. And again, it has to do with the amount of energy that's put into manufacturing these materials, allow them to survive in much harsher environments. And what you're looking at right here are what is called heat exchangers and microreactors that are made out of silicon carbide. This is a brand new technology that has never really been developed anywhere in the world. And what it allows is to have certain liquids passing through some channels and other liquids passing through the others to transfer heat and remove process heat out of severe chemicals. And they'll survive up to over 1,500 degrees C, which is really hot, and nothing else in the world can really do that. I just find all this stuff very fascinating. I hope you guys are finding it somewhat interesting. Another really cool area that every computer relies upon is the manufacturing of semiconductor chips. Certain ceramics are used in wafer fabs because they resist the plasma and they don't create particles when they're going through these high temperatures and all the etching processes. By utilizing advanced ceramics, such as aluminum nitride or silicon nitride, it allows for larger and larger wafers to be manufactured more efficiently, and they're very hard materials, so it allows the planarity of the wafer to stay very planar. And this is what some of the parts look like. So you can just imagine a large silicon wafer there with all of the dies on it, and it's just really incredible that these materials exist and enable technology to move faster and every day. Another area that ceramics are used in is the manufacturing of aluminum. The aluminum industry really uses up about 1.5% of the electricity on the entire North American electrical grid. And by utilizing different ceramics that are conductive and resistant to certain materials, it's enabling them to save a lot of electricity and allow them to have a much more greener process. The materials that are used here is titanium diboride, and silicon nitride, and boron nitride. Boron nitride is a white powdery type material. They call it the white graphite, and it's very smooth, and it can be used on coatings for whenever you need to cast anything, or lots of other really interesting areas. Another picture didn't make it, such as cosmetics. So not only are some of these materials used in these very intense furnaces for manufacturing steel and aluminum, they're actually also used in makeup for anybody who wears makeup. I have a sample up here if anybody wants to look. I think somebody in the audience might. Also, silicon nitride is used for oil exploration and recovery. This material is non-magnetic, and it allows for very interesting electrical equipment to work at thousands of feet below the surface. It actually goes, in some circumstances, to 5 to 10 miles down the earth, down beneath the surface of the earth, to help different companies find oil. And it's just remarkable that anything can withstand the kind of pressures and temperatures that exist at that level. And it's also used in different valve systems and valve balls and bearing balls. And I also have one of those up here that I can show, that you can come up and take a look at afterwards. Every car has brakes. They're machined with silicon nitride. It's the best material to make brake rotors. It just happens to work very well. So every time I stop my car, I thank silicon nitride, at least a little bit. Also thank my response time. Very recently, on another topic, the National Academy of Engineering had its Congress just last month, and it's a team of some of the world's best and brightest minds. Larry Page is actually on the committee of the National Academy of Engineering, and they determined the world's top challenges for the 21st century. They were engineering challenges they are engineering challenges that have no solution yet. And some of them are to making solar energy economical, providing energy from fusion, or figuring out what to do with all that carbon dioxide in the world, and managing the nitrogen cycle, and so on. I have a good feeling that ceramics are going to help solve at least one or two of these problems. And at least from the first problem, the solar energy, some materials such as fused silica are used to make crucibles, to make very cheap and efficient solar cells. Basically, each crucible is filled with an ingot of molten silicon that solidifies and crystallizes, and it's sliced to make a solar cell. And no other material works quite like this. So there are things that are happening in the world to make solar energy at least cheaper for now, and hopefully there'll be much more jumps in technology to make them even more efficient. Just overall, in the quest to make the world greener and to use less energy, ceramics are enabling many key technologies like the windmills, the solar cell manufacturing, nuclear waste containment, and oil exploration and recovery. No matter which way you look, any extreme application needs materials that can withstand those environments. And ceramics tend to be some of the only materials that can withstand the extreme environments. So, tying it all together, ceramics have been around since the beginning of mankind. Really, the Earth is a big rock hurling through space, which is really ceramic. And as technology evolves and progresses, the world is going to use more ceramics, and technology is going to keep going ahead at a faster and faster pace. I brought some parts that you guys can pick up and touch and see at the end. I brought the silicon nitride bearing. I've brought evaporation boats, boron carbide, an armor tile, and an armor chest plate, and also something I made in college, which is glass fulgurite, which was made by harnessing the power of lightning and channeling it through a bunch of different materials, and it creates a hollow tubular formation. So I brought that for you guys to see as well. Thank you. And does anybody have any questions?
So one question, you talked a lot about how energy intensive all this all is, and energy seems to be going through the roof. What does that imply?
Well, it doesn't imply too much. It just implies that they're not cheap. Ceramics always cost more if you need to buy them than typically steel or plastics. But other than that, not much. It takes a lot of energy to run the lights, computers, but it does. What I like to think about is just that it takes so much energy to put into it. It's all stored inside the bonding of the ceramics, and it makes them stronger and last pretty much forever. Yeah.
So normally in chemistry, you learn that the bonds that have no energy are stronger because they're at the bottom of the energy well. Mm-hmm. So are you sure you're not just instead trying to overcome an energy barrier and falling back?
Oh yeah, of course. You are definitely overcoming energy bars, but the level of that energy bar is a lot higher than a different material at a different lower energy. I mean, do you ever overcome the higher energy to get to this hill rather than a hill down here to that hill? Okay. Well, thanks. You come on up and take a look at some of these things if you like.